All right, this set of notes comes out of North Dakota State, their electrical engineering department, and it's a very, very good set of notes. I posted the written set of notes online, and rather than use some of the PowerPoint slides or write my own set of notes, I thought I would go through these because I think this does a really good job. So basically, what this lecture does, first of all, is it summarizes this property of the Laplace transform, that the Laplace transform of the first derivative of t is s f of s minus f of 0. Of the second derivative of t, it's s squared f of s minus s f of 0 minus f prime of 0. So I want to show you how to apply this. So first of all, in general, if we look at a second order initial value problem where we have a second derivative of y, a constant times a first derivative of y, and a constant times y equals some function of time, and then we're given the two initial conditions where the initial condition on y at 0 is y0 and the initial condition on y prime at 0 is y1. So this is basically what you need. You need the differential equation and then you need the initial conditions. So basically what we want to do is we want to take the Laplace transform of both sides of this equation. So we'll take the Laplace transform of the left-hand side and we'll take the Laplace transform of the right-hand side. And so right now, this is just some arbitrary function. We have not specified what it is. P and Q are constants. So if you go and look at properties of the Laplace transform, we're applying a couple of properties here between line 1 and line 2. So the first property, and we're actually applying them simultaneously. So one of the properties is to remember that the Laplace transform of the sum is the sum of the transforms. So we've spread out the transform to each term. And then another property is that multiplication by a constant carries through to the Laplace domain. So P and Q are just pulled out in front of the transform as constants. And now what we're going to do is we're going to substitute for the second derivative, for the transform of the second derivative with respect to time. We're going to substitute with this, the Laplace transform of the second derivative. So for this first term, we've substituted the s squared times the Laplace transform of y, which of course is just going to be y of s. And then here's s times y of 0, which is our initial condition. And then here's y prime of 0, which is our other initial condition. And then we do the same for the first derivative, the transform of the first derivative. And so that's substituted here. Here's our constant p. Here's the Laplace transform of y minus p times y of 0. And then on the right-hand side, once again, we have the transform of f. So in this third line, what we're doing is substituting for the initial conditions y of 0 and y prime of 0. We've already defined that as y subscript of 0 and y1. So that's what this line is. This line 4, we're just substituting the initial condition on y of 0, and we're substituting the initial condition on y prime of 0. And then finally, in the last line, the Laplace transform of y is just y of s, which is just the function that we're trying to solve for. And then the Laplace transform of f is just f of s, and that's going to vary depending on what f was. Now what you can do is collect like terms and isolate y of s. So now I have y of s is equal to all of these terms in s, including f of s, which would be some function of s. Now what makes this a good thing is that now you have a function of s over here. You can take the inverse transform and actually solve for y of t. So you actually haven't had to apply any of the differential equation solution techniques because you've basically taken the differential equation, you've transformed it to the Laplace domain, and then when we take the inverse transform, we'll get an expression for y of t. So I will leave you to read a little bit of the explanation where basically this person just says exactly what I just said. And let's come and look at an actual example. So here's an example of a differential equation, y prime minus y. It's inhomogeneous. I have e to the 3t over here. And we have an initial value, y of 0 is equal to 2. So what we're going to do is we're going to substitute using the expression for the derivative y prime. So we get sy of s minus y of 0. And then y of t will transform to y of s. And then over here on the right-hand side, e to the 3t, if you look that up on the table, that's going to be 1 over s minus 3. So now, if we come one step further and start doing some algebraic simplification, we find that we get this expression. And given this expression, we can then do a partial fraction expansion on this second set of terms. So we basically can get this first term, and then the second set of terms, the partial fraction expansion yields this. Now, partial fraction expansion is a common step that's done before taking the inverse transform. The goal is to get each term to be a first order term or a second order term with a known transform. So we want to get it in the format that we could look up in the table. So in this case, we actually have 3 separate terms. The inverse transform can also be distributed across each term. Actually, the first and the second term have the same denominator, so they can be combined. So now we take our term by term, we take the inverse transform, and when we do that, we find that this one gives us 2e to the t. The minus 1/2 comes through the inverse transform, and then from the table, this is e to the t, and this is e to the 3t. So we substitute back in terms of time, and then collect and combine like terms, and we have an expression for y of t, 3/2 e to the t plus 1/2 e to the 3t. And that's it. We don't have to go back and obtain a particular solution. We don't have to go back and substitute in initial values. There are no unknown constants because basically when we made the substitution for the derivative using the Laplace technique, we already accounted for the initial condition. And on the right-hand side, when we took the transform of e to the 3t, we already accounted for the inhomogeneous part. So it is just done. This step here, where you actually expand y of s into partial fraction terms, that can be done using MATLAB, and I believe there should be some video explanation up for how to use MATLAB to take an inverse transform and do a partial fraction expansion. If there's not, and if you want to learn how to do that, please just let me know. All right, so let's look at another example. This is a second order differential equation, so we require 2 initial conditions. So y at 0 is 1, y prime at 0 is 0. We're going to take the Laplace transform here. So we're going to get s squared minus 3s plus 2 times y. And then this minus s plus 3, that comes from the initial condition substitution using, once again, if we come back up here and look at this second derivative expression, we're going to have a y of 0 and a y prime of 0 that come out of that. So when we make the substitution for the initial conditions, we won't have a y prime because it's 0. Y of 0 is equal to 1, and so that's where this minus s and 3 come from, is when we made the full substitution including the initial condition. On the right-hand side, we have e to the 3t again, so that comes in as 1 over s minus 3. Now what we do is we see we have y of s here all by itself, so we algebraically solve for y of s, and when we do that, we get the following expression. So once again, given this expression, we can either use partial fraction expansion techniques, or we can use MATLAB in order to get y of s written in the following form, where a, b, and c can be found from either analytical techniques for partial fraction expansion, which you have quite a few notes on, or by using MATLAB to do an expansion on this. So once you do that, then you will have numbers for A, B, and C that you can substitute in. Taking the inverse transform according to the table, you're going to get the same expression. So that's that. That's pretty straightforward. Here's another example. I'll leave this for you to read through. It's quite similar just a different expression, a different inhomogeneous part, following exactly the same track where we substitute in for the second derivative and first derivative as we take the transform. We find when we get y of s, we have the following expression. And then once again, doing partial fraction expansion, we can do that and we get 4 terms. And when we then take the inverse transform, we get the following. So the Laplace transform is a very powerful method to solve for initial value problems, both homogeneous and inhomogeneous.